All right, so good morning. Today we will introduce material on adversarial environments, and I will be releasing project number 3. I'm going to work on a little bit more today and probably post it sometime in the evening today. I have two meetings after class today, one with a student and one with the administration about stuff. So that's going to delay a little bit of what I had planned. But before we begin, the usual administrative bits, of course, the reading has changed. Project 3 on adversarial search will be released this evening. The plan is to have it due on Tuesday, the 24th of this month. Some other data points for you to pay attention to. Written exam number 1. The plan is to have that Thursday, the 26th, which is right before spring break. Spring break is the following week from the 2nd of March through the 6th of March. My style is not to have work, at least not for me, over breaks, right? I feel you've earned that and you need some time to relax. But I can't vouch for my colleagues in the department. Everyone has their own thoughts about that. But nonetheless, also, I'm not sure if you're on CS interest and CS majors. There's an opportunity I sent out. If not, just send me a Slack message and I'll send it to you. But I have no um, way of knowing who is actually on those lists. But there's an opportunity at Vanderbilt, it has a medical school in Tennessee, at their biostatistics department. They're looking to hire undergraduate interns, and it's paid. I think it's 4,000 over the summer. It is limited to U.S. citizens and permanent residents. So if you qualify, please do consider it. They're looking for people, particularly who have programming experience, computer science experience, and math/statistics experience. And in their ad, and it came to me by way of a friend, you should have at least 1 year of experience in your program. So it's a data point. If you haven't applied for internships, jump in, the water's fine. I would be misleading you if I didn't say that it is a bit more difficult this season for internships and jobs. So it is a numbers game. Don't take it personally. Just keep putting your stuff out there. And honestly, sometimes you find you apply to the same opportunities more than once, right? Don't take no for an answer. And so that opportunity is out there if you're interested and you are not on the various mailing lists. Please shoot me a direct Slack message and I'll send you a link to that opportunity. Okay. All right. People applying for internships. Yeah. It's really important. It's a little bit more difficult these days. And do consider if you're able to, an internship outside of the United States, right? I get those messages all the time. Come to New Zealand, come to Canada, come to Germany, right? So do consider it. An intern is an intern, right? All right. Any questions about this? No? And also, please bear with me, relatively new to Gradescope. So thank you for all your submissions. What happens underneath the covers is the questions get clustered together, and then you you grade different clusters, if you will, of solution approaches. So on the back end, there's a little bit of a process behind it. So I'm hoping to get that done over the weekend, among very many other things. Okay, so no questions? Any questions? No? All right. Why don't we jump right in? Okay, so hopefully, oh, he's not done. So the next one, to warm you up, why are there no 4th of July knock knock jokes? No, I had to dig deep for this one. Why are there no 4th of July knock knock jokes? Why do you think? No, because freedom reigns. Anyways, all right. So I have some videos it took me a moment to get that one done. And I have some videos for you to motivate our question of the day. And these two videos are from a set of robotics competitions in Singapore. And this one concerns sorting objects, so I'll just play it. And we can chat a little bit about this one and the next one to motivate our question of the day. Pay attention to where these different objects are being placed in the robot. It's not predetermined where these objects are. It's actually getting percepts from the environment and localizing these objects. And then you'll notice at the bottom of the video, there are some receptacles that are color-coded, and it deposits those objects based on color into different receptacles. Okay. So let's go to the next one. And as my friends tell me, it's not soccer, it's football. And this is a robot soccer competition, also in Singapore. 5-on-5. Completely autonomous. I would love to have a competition like this here. Logistics is a real thing. Okay. So, question of the day to motivate what we're going to talk about. Um, which of these problems would you say is quote unquote easier? What would you think? Which is easier, Elliot?
Include sorting because they're able to stop and like make each decision one at a time. Whereas the football, they're already also the place, the adversary, but that like things will change without it being necessarily directly by each individual agent.
So as you decide what you're going to do, things in the environment around you change. Okay. All right, great. Answered why. Um, so they're both continuous, right? They deal with real valued quantities, both in terms of estimating state as well as the actions, right? We talked about some of the pathologies and considerations involved in having a continuous, excuse me, a continuous action space. And as Elliot alluded to, sorting is static. You sort of take a picture of the environment, close your eyes, think about what you're going to do. Nothing changes when you're deliberating. Whereas in football, things change, right? But things also change in a different way. And that change in football is special in that those other entities, those agents that are operating in the environment that are different from you, or in the football case, on the other team, not only is the environment changing, it's changing in a way that's directly in conflict with the goal that you're trying to accomplish. Because if you score, well, that's your goal, right? You want to score points so that you can win the game. But I want to act in a way that's going to directly minimize or conflict against what it is you're trying to do. So it's different from just the environment changing. This change is quote unquote against you. The goal is conflicted. For me to achieve my goal means that you're not going to achieve your goal. And at every move, you see that the environment will be perfectly, quote unquote, against you, right? So that's what's different in this particular case. And so those are called adversarial environments. It's not just that the environment changes, is that it changes in a way specifically to try to detract you from your goal. In fact, for your goal to be damaged, so to speak, in order for me to accomplish my goal. So let me ask you a couple more questions to motivate what we're going to do. We talked about breadth first search, depth first search, A-star search, uniform cost search. We talked about a lot of searches, so-called systematic search. Would something like a systematic search work for this type of environment or adversarial environment? Share your thoughts. Would it work? Can it work? Should it work? Chris?
I would imagine that it probably could work.
Wouldn't be guaranteed. And so in order to have this idea of a guarantee, right? And you're right, there is no guarantee because your adversary may act against you in a way that you lose. Your adversary may act against you or against your goals in a way that there's a draw, right? And so let me ask you this related question. Will local search work? We have this myopic view of what's going on, just your current state and your immediate successor states. What do you think, Nikki?
I think we'll see once they see it. Sorry, forces.
So at each try, because you're kind of looking again, right? You're measuring percepts that it can work. Okay. All right. And so some definitions. When you have a large group of agents and they have conflicting goals, that's called an economy. A lot of this work happened because of economic theory, right? But nonetheless, an economy, it's a difficult thing, multiple agents, a large population acting against one another. And so in some treatments of an environment where you have adversaries, these other agents that conflict against you or conspire against you, if you want to humanize it, in accomplishment of goals, sometimes that adversary is folded into the environment. And if that's the case, because you have no control or notion of how the adversary is going to act, you just see things happen, it's non-deterministic. You can think of it as being non-deterministic. So effectively, from the perspective of one agent on a team, they might think, gosh, this environment sure does change in strange ways, the transitions. Because I try the same action again from the same state, all of a sudden, something completely different happens from the last time I noted it down in my accounting for how the environment transitions from one state to the next. So what that means then is we need to specifically add new information or other information when we model this type of environment, our so-called adversarial environment. So yes, search will work, but this version of search needs to include in the model the actions both for the agent as well as the adversaries for that agent. Does that make sense? And so this leads to a so-called adversarial game tree. And a game tree is nothing more than a search tree. And this search tree proceeds in rounds. In this simple case, imagine we have two players. We have the first player, and that's going to be the agent. And then we have the second player, that's going to be the adversary. So knowing that this game proceeds in rounds or turn taking, we have a step or a state corresponding to the agent, player one in this example. And then when we transition, it's now the adversary's turn to make a choice. Now, of course, we know that when we characterize an environment, we can encode and represent all of the admissible actions or the possible actions in each state. Okay. So we know that this other player, this adversary, can certainly choose from among them. We just don't know which one they're going to choose. Okay. So in that case, in this particular visualization, we have player one chooses an action, action A, B, or C. And then on the next turn, it's now player two's turn. So from the perspective of player one's decision is going to be influenced by all of the different ways that player two can act. So when player one decides, I want to achieve maximization of some objective, right? It can't just maximize the objective. It has to contextually consider whether that objective includes player two taking action A, action B, or action C. So you can almost think of it as a kind of scenario testing. And as you can imagine, as you add more adversaries, this can get very big very, very quickly. Any questions? No? And so the notion of an evaluation, we've been talking up to this point about reaching a goal state. Now, in this case, our evaluation becomes one of, is this person winning? Who's winning? Who's ahead? And we talk about notional terminal states. And that terminal state corresponds to the end configuration of that game, that interaction between an agent and its adversaries, the end of that game. And that could be a win, okay, the player wins. It could be a loss, the agent or player loses, or it could be a notion of a draw, okay? All right, any questions? No? So instead of goal state, we're going to talk about terminal state because at some point this game has to end and it can end in a win, lose, or draw. And so we have an evaluation function, and it's the goal of this evaluation function to examine features of the state. In football, okay, is that orange ball inside of the goal? Yes or no? In some other type of problem like Pac-Man, well, are all of the food pellets eaten? Yes or no? And so this idea of evaluating terminal conditions is related, but it's not the same as saying, have I reached a goal state? Because along the way, you're not guaranteed that you're going to reach the goal. What you are guaranteed is that the game will end. So you have to describe features that describes the different ways this game, this interaction between the player and the adversaries will end or can end. Does that make sense? Any questions? No? All right. And so this is a two-player deterministic game, proceeds in turns, and each turn is called a apply, right? It's each player taking a turn, right? A particular player's time to choose an action, opportunity to choose an action. And that could be an action, and in some games, it's a no-op. I'm not going to do anything. Pac-Man's just going to stay put, for example. And so in this case, simple case, it's fully observable. That means at each state, you can view every aspect of the environment's configuration. And this type of game is called a zero-sum game. What it means is that we assume each one of the agents, the player and the adversary, are making optimal moves. And what is good for the agent is bad for the adversary. And what is good for the adversary is also bad for the agent, right? So there's no win-win here. Somebody wins and somebody loses, and absolutely you can reach a terminal state where it's considered a notional draw, right? Sort of nobody wins. Does that make sense? All right. And so a lot of what we're talking about now in adversarial search has to do with zero-sum game type of games, meaning that it's assumed that all agents will act optimally at every ply. Now, is that always true? No. Sometimes it might be of value to make a suboptimal move. If you have an economy, more than two agents, maybe two adversaries might decide, gosh, well, the agent looks like it's on a pathway to winning. Let's make some suboptimal moves in collaboration to try to confound this agent. So, sort of like the enemy of my enemy is my friend, so to speak. right? So absolutely, you can make suboptimal moves, but the assumption at this juncture for the treatment of this adversarial representation is that it's a zero-sum game and both of the agents always make optimal moves at each turn, at each ply. Okay? Now, absolutely there are relaxations, but to introduce the concept, we have to make this simple case. Okay. And so sometimes they use synonyms for things. An action is often called a move because it is a game. And sometimes the word state, which we all know now, is referred to as a position, right? And I will also sometimes say node as a synonym for state. That's just old habits. Okay. And so you have two players. These players are designated nicknames, if you will. One is called Max. We have a Max in the classroom. And one is called Min. And they alternate between taking turns or plies. Max acts, and then it's Min's turn, and then it's Max's turn, and then it's Min's turn until the game's over, right? Win, lose, or draw. And so in each case, you'll notice at particular depths or layers, if you will, in the tree, we have a node for player one, and then the next layer in the tree or at depth one is player two, and then the next layer is going to be player one again. Okay? All right. Any questions? No? All right. And so it's called MINIMAX search, minimize and maximize search. Okay. And so let's give some definitions. These are all from the book. We start in an initial state, and then we add a method called toMove. And toMove returns, but you give it a state, and it tells you which player's turn it is in a particular state, in each state, because that's going to change, right? So we need that routine. And then we have actions, which tells you all of the legal moves in a state. And one of the things you'll see for something like tic-tac-toe, the number of legal moves is going to reduce as you continually fill the board between the player that writes the X and the player that writes the O. Okay. All right. Any questions? No. And then we have results, SA. That's your transition model. It accumulates for you all of the outcomes of taking an action, A, in a particular state, S. And so you're going to build that over time. Then we have is terminal. And it's not the same as is goal that we've been talking about before. And is terminal tells you whether or not the game is over in that particular state. And this is where you evaluate features of the environment to determine what is an ending condition. When is the game over? Does that make sense? Any questions? No? All right. And then lastly, we have utility. This utility function in some pieces of literature, you'll see it called a payoff or an objective. And it's just like the objective functions that we talked about before. This is this notion of a final value for a given player in a particular state, as terminal state. Now, you can have utilities for non-terminal states, but it's a little bit wonky because sometimes you might make updates on that. Okay. All right. And so this is an example, it's from the book, of a tic-tac-toe board. And just by the convention here, we have Max is the person that places the X's in the tic-tac-toe board. And Min is the agent, the adversary that places O's in the tic-tac-toe board. So we start out with a blank board. And here you can see the expansion or partial expansion of the entire search tree over the graph of states, where the state represents all the possible configurations of the board, beginning with the start state where the board is empty. And so Max makes a choice. And as you can see, that choice is to place that X in one of the 9 many spaces that are possible. And for each choice of Max, okay, Min is going to make a choice on the next term. And so Min says, okay, well, given that, I can make another choice. Now, if you're Max and you're trying to decide what move to make, Max can't just look at all the places it can place an X. It has to consider all of the outcomes of actions that Min can make in placing an O and Max's behavior changes in terms of which traversal down this game tree is going to lead to or can lead to an advantageous terminating state based on the actions of men. And so you can't just act on the environment, you have to act based on what you know to be the different outcomes of your adversary. And so it's your adversary's actions that dictate what optimality means. Does that make sense? Okay. And so here, with this turn taking, we have 9 choices for the first move, 8 choices for Min's move, and then 7 and 6 and so forth. And so if you were to enumerate all of the possible choices you can make, you might think, gosh, that's 9 factorially many, right? Okay. But that's not the case because depending on the choice that you make, you don't have necessarily all available configurations from that 9 factorial available to you. But nonetheless, this 9 factorial is an upper bound on the number of terminal states you can reach because sometimes for some of those pathways through the tree, you're going to get 3 in a row and it ends prematurely. You're not going to go ahead and seek all of those 9 factorially many configurations. Does that make sense? Any questions? No? So, of course, with the treatment of this material, you're always going to see simple examples to illustrate the point, and it can get very big, very, very fast. All right. So Max wants a sequence of actions for a win. Min also wants to win, and Max's plan, those actions that Max pursues in the game tree, is going to be conditioned on Min. And so this is called a MINIMAX search, right? From the perspective of Max. I mean, you could absolutely do it from the perspective of Min. It's just that the one that starts first in this example is the Max. Okay. All right. And so this is an abstraction, a MINIMAX search tree. And in this visualization, all of the up pointing triangles or the purple triangles, those are so-called max nodes. That's a choice point for a state for the max player. And then all of the downward pointing triangles, that looks like red or orange, red, let's say red, the red triangles, those are so-called min nodes. Those are choice points for the action that the adversary min is going to be playing. So each player gets a turn. And as I alluded to before, as I jumped ahead, apply is the turn for single player. And so you could say this is a 2-ply game, or you could say a turn represents apply for the max and apply for the min. So whenever you see the term ply, that means a single player's choice point, opportunity to select an action. And that selection of the action, if you're max, considers what min would do. And if you're min, it considers what max would do because the two are linked together. Any questions? No? Oops. So there's a quantity in the book called MINIMAX. It is parameterized by a state, and it gives you a notion of utility, this measurement scalar of usefulness for winning or usefulness for an advantageous terminal state. And so this is a utility for Max being in some state S. And the players, again, it's important to the framework, are assumed to act optimally until the game terminates. Okay. And so minimax of a terminal state is its utility, but for a non-terminal state, you might have sometimes to do other things because you're going to update that quantity. And I'll explain about that in a few more slides. Okay, any questions? No? Okay. I don't have my headset. I keep forgetting to plug it in, so I'm not going to wander too far from the lectern. If you're a non-terminal state, then Max wants to move so that it gets as big as possible of value, the score, as you will, upon its turn. So it's always going to pursue those successors that have large values. And yes, a successor of Max is a min node. So it's going to take the best of what this minimum is going to do. And likewise, the min node, it's going to select or pursue a successor, a max node, that is the least of what max would do. And so as you do your search, you're considering at each ply the action of maximizing among the smallest things or minimizing among the largest things, so to speak. Does that make sense? And so here you start out, if you're a terminal node, you return the utility for that particular player. And it's important to note that utility is indexed by the state as well as the player itself, right? And if you're not a terminal node, if it's Max's turn or Max's ply, you're going to call MINIMAX with the result of taking each one of the actions, and you're going to maximize over that successor, that action that leads to the largest value. Likewise, if you're min and it's min's ply, min's turn to move, you're going to find the action that results in a successor that has the minimum value. Okay. Any questions? No? All right. So let's take this example, and this example is in the book. And here we've marked the terminal nodes at the leaves of the tree with utilities, right? So just assume these are the utilities. And so if we start out with node A, this is a max node. And the successors of A, if we examine going from left child to right child in that direction, we have a 3 value for node B. We have a 2 value for node C, and we have a 2 now value for node D. So then A, our max node, is going to select action A1 because that 3 is the largest value associated with its successors. Likewise, node B, it is a min node, and it has 3 actions, B1, B2, and B3. And if we look at the value of its successors, those are max nodes, its successors. They're also terminal nodes. The values are 3, 12, and 8, respectively. And because it's a min node, it's going to choose action B1 because that is the action that leads to that successor with the smallest value, namely 3. Does that make sense? Any questions? No? All right. So node C is min, it's going to select action C1. Node D is min, it's going to select action D3. Again, in both of those cases, because those actions lead to a successor node that has the smallest values, respectively. Okay. Does that make sense? Any questions? No? All right. Sometimes, as I said before, you're not going to take the optimal move, whether it's pursuing the smallest node in the min case or the largest node, because you might want to, in the worst case, cause a draw. You just don't want to lose, right? Okay. And so this is the pseudocode for the so-called MINIMAX search. And in this MINIMAX search, the first thing you do up above is, let me get my pen here. Let's see if I can get this to, there we go. The first thing you do is you check to see whose turn it is. And once you know whose turn it is, okay, you set the player because that's going to influence how you access certain data structures and what you're going to do. And then you go ahead and call max value. So you're going to pursue the action associated with the largest valued successor node. So then you start out and you enumerate all of the actions that are admissible from that state. And you're going to call min value on each of these actions because those successors are min nodes. So then you call min value, and let's just assume min returns the smallest of its successors. We're going to stay in max value for now. You're going to see if that value among those successors returned by min value if it produced an improvement in value, because this is max that we're talking about. So max always wants the biggest things, right? So if you did get an improvement in value, you're going to accept it. You're going to say, all right, well, I want to select that particular move, that action, and I'm going to keep that value, and I'm going to do that over all of the actions that are available. So I'm going to consider my first successor, second successor, third successor, and they just happen to be min nodes. And however they return a min value, I'm going to find that min value, whichever one is biggest, and I'm going to pursue that or return that. Does that make sense? All right. So meanwhile, when it calls min value then does a similar thing. It's going to look or iterate over all the actions that are available, and it's going to call max value on each one of those successor states. Now, eventually, it's going to go down further and further and further in the tree until you reach a terminal state, and then you're going to back your way up with these values. Does that make sense? Any questions? I can see you. All right, past the second row. All right. Let me see if I can release the pen. This thing is a sticky pen. There we go. Okay. And so this looks a lot like depth first exploration, but it's not depth first search like we studied in the systematic version, because with DFS, it was the data structure that dictated which node we picked. We picked the first child, right? But in this case, we're going to do it in depth based on this singular decision, which is the min and which is the max. So it's just like DFS, but the selection discipline is a little bit different. In the case of max, it's going to select the maxed one. And in the case of min, it's going to select the min. All right. So keep in mind, it's like depth first search, just the difference is in the discipline it uses, criterion it employs for selecting which node to pursue. Does that make sense? Any questions? No? All right. And so because it's just like depth first search, well, the time is proportional to the depth, and the space, that's good news, is order BM. Okay? All right. Any questions? No? All right. But as you can imagine, for complex games, yeah, for things like tic-tac-toe, Pac-Man, with a small enough board, it'll work. But for complex games, it can get really big really, really fast. And I had to look this up because I'm not, well, I've played chess, but I'm not like a big chess person. I can still beat my daughter. But nonetheless, the branching factor in chess is roughly 35 per ply. And the depth for a game is about 80 moves. And this gives 35 to the 80, which is approximately 10 to the 123 states, right? That's a big game. And it's really, really hard to represent that in this form in a traditional computer and do all of that search. Okay, so you might need to do something different. That just means you have to prune, right? If you want to make it feasible. But people have solved chess, absolutely, through reinforcement learning and other methods. And we will be doing reinforcement learning in this class. And as we saw in football, well, it's not just one agent. You have more than one agent. And so there's an extension to this basic MINIMAX adversarial representation where you're considering multiple players in a game. And so in this example, it's in the book, imagine you have three players. We're going to call player A, B, and C, or agents A, B, and C. And so instead of having a singular scalar for your utility, you're going to have a vector valued utility. So imagine then if you had, in the case of the football game that we saw with the robots, you have 10 players. Imagine a utility vector that has rank 10, right? But nonetheless, we have each position of this utility vector is associated with the utility from the perspective of each player, okay? And so if you have a terminal state, that terminal state also has a utility. Now, some of those positions by definition of win, lose, or draw, some of those positions are going to be higher values and others are going to be lower values. But nonetheless, you're explicitly representing the utility from the perspective of each one of our players. And so in this visualization, and I'll walk you through some important observations. This is a game tree, and this game tree reflects the multiplayer adversarial environment. One of the things you'll notice along the left-hand column, you're going to see it's going to be A's move. That's that root layer. Then it's going to proceed to B's move. That's that next layer. And then C's move, and then return back to A's move. So in this case, the assumption is that each of the players gets a turn in some order, and we repeat that order A, B, C, A, B, C, A, B, C. So imagine then if you had 10 players, you would have a repetition of each one of those 10 agents in the tree. Again, this gets really, really big, really, really fast. The other thing you'll notice is that each node is decorated with that utility vector. And so when we do our search in this particular game tree, we search from the perspective of each of the agents taken in kind, trying to maximize their utility. So again, it's kind of like a depth-first search, choosing or pursuing that action or that successor associated with the maximal choice for the utility of that particular agent in that moment. Does that make sense? Any questions? No. All right. So I'll direct your attention to this, if you can see my mouse, node labeled X, and let's observe that particular state. So we have two choices. We can pursue the action that gets you to the left child or to the right child, and there are two choices. Now, because this is agent C, we're going to look at the third position of these three vectors, and we notice for the left child, position 3 for agent C is going to have a value of 6, a utility of 6, and for the right child in position 3, we're going to have a utility of 3. And so agent C is going to choose that action that leads to the left child because that maximizes its utility in that moment. So then after that, it would be agent A's turn, and agent A would do similarly, but we've reached a terminal state, so we don't search any further. Does that make sense? Now, this is only just one repetition, A, B, C, going back to A, but you could imagine if we expanded this through, let's say, 5 or 10 moves, right? So that's 15 to 30 layers in this tree. It gets really, really big. But the context matters. It's whichever agent has that particular ply, that's the position in our vector valued utility that we're going to use as the criterion for that selection of which successor to pursue. Does that make sense? All right, any questions? No? Okay. And so that would be the value that vector 1, 2, 6 would get backed up the tree. And then when we're playing the game, if we make an evaluation, well, first of all, we're doing local search, we're going to observe what happens, but we can certainly navigate a pathway based on these multi-agent perspectives. Does that make sense? Because you don't know if you're agent A, you don't really know what B and C are going to do. This is under the assumption that they're all acting optimally. Now, if somebody makes a suboptimal move, you're going to have to alter what you do. Say, gosh, well, that wasn't the optimal behavior I was imagining. They did this other thing. So that alters your search. But under this assumption that every agent acts optimally, you can still construct a plan in the multi-agent case. Does that make sense? All right. And you can certainly adapt and adjust plans based on the percept sequence that you encounter in flight while you're playing the game. Okay. All right. You can certainly have cooperation, which I alluded to before, alliances. If agents B and C if agent A and B notice that C has the strongest position, they could certainly decide to make a suboptimal move, right? With that suboptimal move to try to confound C, forming an alliance, right? The enemy of my enemy, so to speak, is my friend. because it's better to have a draw than it is to lose, right? And you can have a draw easily by colluding with other agents in the environment. Okay. Likewise, these two players might decide, yeah, let's make a draw, right? We have a stalemate. I'd rather you don't want me to win. I don't want you to win. So maybe the best alternative is for us to arrive upon a draw. Okay. And so there's that type of cooperation as well, in addition to conspiring against that agent that might have the strongest position at the moment. Does that make sense? All right. Any questions? No? All right. I really wish this were in the middle because I find like just turn to that side and then. All right. So let's talk about this idea of dealing with the complexity of this tree. Because as you see, it can get very, very big, very, very fast, especially so if you go to the multi-agent case, because now there's a multiplicative number of layers that you have to add to the tree to accommodate the perspective of each of those agents in the multiplayer case or the multi-agent case. And so pruning is always a good thing. And in the systematic approach, if we have something like a breadth-first search that explores all of the nodes in the tree, we said this is exponential. And exponential is always a bad idea, okay? And so the idea then is this idea called alpha beta pruning, which works to prune your search tree to, i.e., not consider subtrees rooted in certain nodes to reduce ultimately the complexity in time and in space. And so it's all conditioned on this vector. This vector, this two vector, has two positions. One is called the min value, and one is called the max value. Okay. And so I always allude to the 80s in my soundtracks, right? And so this essentially says, out of curiosity, anyone know who that is? Oh, man. No? All right. Janet Jackson. Do you know who Janet Jackson is? Okay. Whew. All right. Anyways, but nonetheless, what have you done for me lately, right? It maintains this idea of what is the best minimum value or maximum value that I've encountered throughout all of my search. Because it doesn't make sense to pursue a node if that node's value is less than the max that I've encountered, because that part of the tree, the idea goes, is going to be less fruitful, right? Assuming everyone is acting to optimize. Likewise, if I'm trying to minimize and I find a value that's greater through my search, that's whose utility is greater than the current min value that I've encountered, it doesn't make sense to further pursue that node. So in essence, I can, by tracking this notion of what have you done for me lately, I can use those pieces of information as I propagate them, as I continue to expand nodes, I can use them to ignore certain parts of the tree, thus pruning my search. And this is quite effective. Does that make sense? All right. So here, and I'll walk through this example, we start out with the max node A in frame A, and we set our seed values, the min, I forgot already, min and max. Okay. We start out with our initial values, and we expand our node B from node A, so we're looking at its successors. Now, B then goes and finds the minimum, and the first node it expands is its successor, which has a utility of 3, and it's a terminal node. So we back up that 3. Now, because it's the first time that this min node B has encountered a utility, a node, it says, well, that's going to be my min. Okay. Now, if that's my min, okay, well, I'm going to say, that's also going to be the max that I'm considering. Okay. And I remember that min value of 3. And then I continue to expand my other successors as a min node. So let's say the next successor has a value of 12. Okay, well, that value of 12, it's bigger than 3, and I'm a min node. So I'm going to go ahead and keep my 3, and I'm going to expand my next successor or generate my next successor. And so let's say that next successor has a utility of 8. And that utility of 8, well, 8 is greater than 3. I'm a min node, so I'm going to keep that 3. Now, at this juncture, well, if I know my min is 3, right now for max, the best I can do is 3 because I have a single child, which is B, a min node, and it returned a 3. So max is going to also accept that 3 as its threshold. Okay. So now I go back up to my max node, and my max node expands its next child. And that next child in frame D, let's call it C, it's a min node. And so C then expands its first child, and let's say that first child, as is noted, has a utility of 2. So that C says, okay, well, that's my only successor I have at the moment. So that 2, I'm going to call it my min. So then next, you'll notice here, this 2 is smaller than the 3 that it had before, right? So this 2, it's now the smallest, and it's not going to expand any more nodes because it's like, well, I found this 2. That's my smallest. So I'm not going to explore any other nodes. Let me see up the tree. 3, 12, 8. You get the 3. I have the 3 up here, max. Max sees the 2. And 2, rather, is smaller than 3. And because 2 is smaller than 3, max does not want to pursue any further. That's what I meant to say. So I'm ignoring these other 2 successors under node C because it's not fruitful to explore them. Because I know from Max's perspective, the previous one returned a 3. I'm trying to maximize. So there's nothing out of min that I'm going to take because I already know 3 is better for max than 2 that I just uncovered in node C. Does that make sense? Any questions? No? All right. So now max pursues the third successor. And that third successor is D. And D uncovers its first successor, which has, in this example, utility of 14. Now, 14 is greater than the 3 that Max had from its perspective from when it expanded its first successor, node B. So it says, you know what? This is kind of exciting, right? I have something that could be bigger that was selected from the min node beneath me. So it says, okay, let me go ahead and expand the next successor and the next successor, which is 5 and 2 in kind. Now min sees that 2 and expanded those successors, and it returns back that 2 because 2 is smaller than 14, and a min node always selects the smallest successor. So now I have 2 and 2, right? And Max says, all right, well, the best alternative was 3 because I want to choose the largest of my children. And so essentially what this alpha beta pruning does, it holds on to this notion of the best maximum that I've encountered throughout my entire search, the best minimum that I've encountered throughout my entire search, and then it uses that to either consider pursuing or ignoring successors along the way. Because you're a max, if the min node beneath you returns something smaller than something you've seen before, there's no use in further pursuing anything that's rooted underneath that successor. Does that make sense? Any questions? No? All right. And so this is from the book down below. It tries to use compositions of mins and max to show you mathematically what's happening, and it arrives upon the same result. Okay. So the values at the root are independent. When it says independent here, and when I say independent, I don't mean statistically independent, right? It means that the coupling between them is such that when you make a local decision, you carry that local decision and that influences where you're going to go later on, right? So in each decision is made in kind. So this means you can prune away from the root based on what a node that's further up in the tree encounters. It holds on to this min value and this max value throughout the course of all the nodes that you visit. And the idea is that if I already have a max value, the maximum value, and I expand a node and that node doesn't lead to something that's greater, there's no improvement, so it's not going to be fruitful for me to explore that subtree. Does that make sense? Any questions? And there's some typos in the slides, and I'll point out what those typos are. So this leads to the notion of something called alpha beta pruning. And it says that values at the root are independent of the values at the leaves. And so in this, each layer of the tree corresponds to apply a particular player's move. And we start out with the player. And let's say there's some node that the opponent selects, and it has some best value. We'll call that M. So later on, as we're expanding, switching between the player and the adversary, the player and the adversary, we come down to an opponent, and let's say we have. So then if we see something called N, and N is smaller than M prime, we don't pursue it because its value is smaller. So anything rooted in that node that has this utility N, it's not worth our time. What have you done for me lately, right? And we therefore, in doing so, prune entire subtrees away. And so the key is holding on to this piece of information. You prune by remembering these thresholds, these notions of the min value and the max value. Does that make sense? Any questions? No? All right. And so this is called alpha beta, and I always confuse this, right? Because you say minimax, min and then max, but in alpha beta pruning, think of it as maxi min, right? And with alpha beta pruning, it has two quantities, alpha and beta, hence the name alpha beta search, because it does what's called alpha beta pruning. Alpha, the first value, is the best value at any choice point for the max player, the agent, if you will. And you can think of this as being a floor, right? At least alpha. So I want things to be bigger than alpha. If it's not bigger than alpha or greater than equal to alpha, it's not worth my time. I haven't done anything for me lately, so to speak. And then beta is similar. It's the best value at any choice point for min. And you can think of beta as a ceiling. Because min wants things to be smaller, if you are greater than this threshold beta, greater than the ceiling, bigger than the ceiling, it's not worth further pursuing. Does that make sense? So it's max min, even though you see the algorithm called min and max, and I always confuse that. Anyways, so we have our floor and our ceiling. All right. So this is our alpha beta search. And this alpha beta search is like a minimax search, but it uses these thresholds, these alpha beta, our floor and our ceiling, to cut off the search, to say it's not fruitful. I'm just going to cut and run because it violates either it's less than my floor, it's not worth pursuing, or it's greater than my ceiling. It's not worth pursuing if I'm min. So we start out with max value, and we're going to exhaust all of Max's successors. And remember, Max's successors are min nodes. And we come in and we get min's choice. So because all of Max's successors are min nodes, I ask that min node, okay, what are you going to return to me? Let's assume that it comes back, and the question that Max is going to ask is, does min's selection improve my ceiling, right? I'm sorry, my floor. Does it improve my floor? See, I do that all the time. Does it improve my floor? Does it improve the value from Max's viewpoint? If so, I'm going to take it, right? Because it improved. I want to maximize. Even though min was selecting the smallest things, I want to maximize. And I update the cutoff for my floor. because min found something in this case, my successor found something that is greater than my floor value that I had. Does that make sense? Any questions? No? All right. So then we ask the question, does it violate the ceiling of min? If it violates the ceiling, okay, then we just want to return, right? Because we know after that, the next time we call them in, bad things will happen. We violated the ceiling. So then if we don't get any improvements, we just return after iterating through all the successors of max. Okay, and then the same deal happens in min value, only the roles are reversed. We come in, we evaluate all of the successors. And for each successor, we call its max value. We select the biggest thing. And then we check to see if that max value improved upon our ceiling. If it did improve upon our ceiling, we take it, and then we check lastly to see if we violated the floor, right? And we return immediately if we have. Does that make sense? Any questions? No? All right. And so max exhausts all the successors looking for improvements. We accept it if we get an improvement, and then we stop if we violate min ceiling. And if no improvement, we just return. Min exhausts all the successor nodes, which are maxes looking for its improvements. It accepts it if it finds an improvement on the ceiling, and then if it violates max's floor, it returns. Okay? All right. So we're switching back and forth. And so in this case, from min's viewpoint, to go back to that example that we had, we notice here that we generated that first successor that had a utility of 14 in this min node, right? Now, if we were able to look at all the successors and order them in non-decreasing order in terms of the utilities, we could kind of arrive upon this solution faster, right? A so-called killer move. The killer move approach says that rather than spend time, evaluate the first successor, back it up, evaluate the second successor, update, evaluate the third successor, update. If I generate them all, get this vector of utilities, sort them, I can immediately now pick this notion of a best move without that analysis. But the burden then is just the evaluation of the utility for all of those successors. That's a so-called killer move. So even with this, there are some optimizations that you can make when you do alpha beta pruning, but certainly if your successor space is really large, you have a large number of successors, there's an additional burden of the cost of the generation, evaluating the utilities and the sorting of them in some order. Does that make sense? Okay. And so there's another approach called heuristic alpha beta pruning. And with that, it's the same as our alpha beta pruning, but we're going to just add an estimate now instead of the utility itself. And so essentially what we're doing with this estimate is we're trying to cut our search early using an estimate for our utility. Okay. And so this cutoff is going to be true for terminal states, but for non-terminal states, we have to have some type of evaluation criteria, like you design for any heuristic, that is a good estimate of what utility might mean. Okay, now this could be a set of properties, and we'll talk about that in a couple slides if time permits. But this is called heuristic minimax search. And with heuristic minimax search, if we have a cutoff, then we produce the evaluation, which is the exact utility of that particular state for that player in question. If it's Max's turn, then we recursively call H minimax, our heuristic version, with the next state from our transition model, results SA, increasing our depth. Likewise, if it's min's turn, we then find the action that minimizes our recursive call H minimax using our transition model. And in this example, this is the sort of first approximation. In this example, in the book, they talk about a function of depth might be your estimate for what utility it is. Does that make sense? So it's a recursive call that pursues the single best, but the difference here is that we're using estimates of utility and not the actual utility itself. Okay? All right. So our estimate then would be somewhere in the bounds between utility of a loss and utility of a win. It's up to you to decide what this estimate is. And so this utility estimate should have some features that it extracts from the state description about the possibility of winning. And so you use a bunch of resources to do this. And in chess, and I'm not a chess player, you might count through some proportion the number or the value, the material value, so to speak, of certain types of pieces. And so you might count, for example, for an estimate of utility, the number of pawns, the number of queens, the number of knights, the number of is it rook bishops or whatever they're called, bishops and knights and all that stuff. And that is sort of a proxy, an approximation for the chances of winning, because the more power, so to speak, or the higher the material value of each piece, the more likely it is you're going to win. Will you absolutely win? No. But it's more likely that you will if you have more what I'll call expressive pieces on the board. And again, I apologize, I'm not a chess player. And so in this case, your estimate of utility might be some weighted combination. In this case, these functions for chess would be a count of the number of certain types of pieces that you have. And this combination, in this case, is linear, could be nonlinear. Maybe some pieces contribute more to this function. Maybe some pieces contribute less. So for example, a queen would contribute more than a pawn because it can't move, the pawn can't move the same way. Does that make sense? Okay, but it's up to you to decide this. Now, this is the alpha beta pruning search. And in this case, the estimate just takes your terminal state check and your utility and replaces that with the check for cutoff and this estimate of utility. So literally, it's just a two-line change algorithmically to go with the heuristic version versus the regular alpha beta search. Does that make sense? All right. And so with this heuristic, you can actually design a lot of things, right? I had alluded to what I called the boo factor, which I wanted to show you as an exercise, this idea of closeness to the ghost as a feature from the environment that you can use in the adversarial version of Pac-Man. So maybe I'll do that not Friday, but maybe next week Friday, depending on how the semester goes. All right. And so we have about 3 more minutes left. I'll end with this. Let's start looking at considerations for adversarial version of Pac-Man. In this example, imagine we begin with 10 points, and for each turn, we lose 1 point. And the idea is to consume the food pellet and get the most number of points that you can. And so in that case, you don't want to spend that many moves in order to get to the food pellet, okay? Well, in this case, if we go straight to the pellet, starting with 10 points, that's 2 moves. 10 minus 2 is 8. So that means 8 points is this utility that we're seeking in the Pac-Man environment. And so certainly, if we backtrack, meaning if we go someplace else beyond, instead of directly approaching the pellet, we're going to end up getting less than the optimal 8 points for our utility. And so this means we need some other piece of information. And this piece of information is a value function. And we'll see this idea of a value function reoccur in reinforcement learning. And this value function is going to encode the utility of each state. And so in this expansion, you can see for the left-hand child of our starting state, Pac-Man goes away. And for the right-hand child, Pac-Man goes towards the pellet. And as we go to the next layer of the tree, Pac-Man goes to the goal, and the utility of that state is 8. Does that make sense? Given this game parameter. Okay. So if we look at the recursive structure, we try to take an action in the next minute that's going to maximize the value. So we're going to choose an action that leads to a successor, and that should maximize the value. And of course, we know what the value is for the terminal states, and we can certainly back that up as we make our choices transitioning. We know that we subtract 1 point for each move that we make. So we can actually construct this and pursue this optimal path. And I'll end with this. When we add an adversary, we're going to be adding complexity to the problem, because now Pac-Man's actions, starting in this root node, the blue squares are Pac-Man's action. The red nodes, or the red circled nodes, are the ghost's actions. And so Pac-Man should want to take or pursue the right-hand child, but that's going to be disadvantageous because Pac-Man is getting closer to the ghost. And so the optimal move here for Pac-Man is influenced by what the ghost is doing. So Pac-Man is best served to maybe move away from the ghost, even though that goes against the goals of Pac-Man. But if you're doing MINIMAX search, it could be, you'll notice here, if we take the right child, when it's Pac-Man's move, gosh, well, that's not going to work out too well because you're going to lose the game. Does that make sense? So we will pick back up tomorrow. Oh, we're over by 30 seconds. So we'll end there, and I'll see you all tomorrow. Have a great, see you tomorrow. Have a great rest of your week, but you'll see me tomorrow.